Cool, thanks everyone. Nice segue from Zach, but yeah, here is Lukas. Lukas was down in our London office recently, whiteboarding with the rest of the team. I think a lot of hot ideas there, so interested to hear what you got, Lukas.
Guten Morgen. Hi, everyone. It's great to be here. I've been at all 3 NoirCons, and this community is really something special to me and us. I first felt this during EFCC last year at the Trust Infrastructure Day. And again, in full-blown effect at a rather spontaneous workshop where we could come together at the Aztec office later in the summer in London. And from this very tight group and this really nice people, it's amazing to see how the community evolved over, it's only 10 months now. And today I want to talk to you about something I believe is critical where we go next. Around 2 years ago, I was at the Science of Blockchain conference, walking around with a question in mind. At that time, everyone was talking about CK in the programmable cryptography land. And it felt like a bit off because people were kind of alluding that CK would solve all the problems that we are attributing that can be solved with programmable cryptography. But this doesn't felt right for us. Why? Because CK doesn't let you, for example, collaborate on private data. It's inherently stateless. And most valuable applications on the internet today, from marketplaces to messaging to governance, are all collaborative and stateful in nature. So I spent the conference asking everyone, are you thinking about the limitations of CK? And here I mean the limitations of CK beyond performance and developer experience. Turns out most didn't. Everyone was really focused on proof system and lookups. This was the time the first open CKVM, Lasso Jolt came out, and also zero knowledge machine learning, or CKML, was at really its hype cycle, even though ChatGPT didn't come out so far. Now, CK felt just synonymous with programmable cryptography. And this bugged me. Why is no one seeing the obvious, or is it us that we are just dumb and don't see how this all works out in the end? Then on one of the last days, I met a person who was the head of cryptography for a big project that's just launched. And we were talking, and they were already using Ethereum as their root of trust. They were using client-side proving CK all over the place. But they only have launched 1 or 2 months before and already ran into the problem we were alluding to. They needed confidential compute. And they couldn't find any infrastructure that they can use. Even worse, they couldn't even find tooling that met their requirements. And that's the case because confidential compute in general had been overlooked and neglected for years compared to CK. So this moment validated what we felt. Something fundamental was missing. And most didn't see it because either their projects didn't launch and didn't run into these problems, or they were just too deep into CK narrative that CK would solve everything we need. To sum up, in a world let's pretend CK has no overhead and we can program in Angular language and you can even vibe code it if you want. If we do not get confidential compute as a second pillar, we'll never reach the full impact we want. Now I want to zoom out a bit how to see this observation of the CK space fits into the broader blockchain and internet space. We often like to describe the internet in 3 phases. The read phase, the early web where you could browse, you get your information. And the second phase where the read-write, where we're currently, the Web 2, you can participate, you have social medias, you have marketplaces, you can text people. That's really what most people are using today. And we know all that we have built great networks in this internet, but those networks got more closed over time and more extractive. So we need something different. We all agree on that. And that's sometimes called read-write-own, sometimes Web3. And at the heart of it is that users, content creators should take back control and that the networks should be positive sum and open. And at the heart of it are blockchains that make this possible. That's at least a promise. But real control isn't just about self-custody. Self-custody is not enough. It's also about how your data is being processed and who is processing your data. If you're looking at Web 2, like how do we do that? Like we get some kind of privacy in Web 2, like at least we have privacy from our peers in Web 2 applications. We get this by trusting or an operator like Google, Meta, or whoever runs the application. If you're building an application currently on a blockchain, it's even worse. Like if you want to handle some form of private data, your options are quite limited. You either disclose everything, which is worse than the Web 2 model so far, or you go back, taking the data off chain and trust, just like being a trusted operator like Web 2. And you can't blame the app builders for that. There's no infrastructure. There is no infrastructure for secure, scalable private compute. And we need that more than ever today. Like AI, we all know, is changing how we interact with information, with each other, with the web. Like the open internet, at least for me, is collapsing into a prompt bar. And this is a huge centralization force. We often describe, or we hear that like blockchains are this kind of counterbalance, counterweight to these centralized tendencies for AI. But for me, this doesn't make sense, at least not now. Because like blockchains today can't handle private data, so how would they handle my prompts? Some people say, yeah, just run the AI locally. But I think this goes beyond the point. Like we're seeing already that if you want to have like a really powerful AI or large language model, a lot of advantages gained by having memory, context over time, over your habits, your programming habits, or like whatever you do, like how you interact with an LLM. So you need this context be across devices, across sessions, across models. And we already can see this will default back to the cloud. So what we need is a network that let us store, access, compute, and collaborate on private data without giving it up. Without that, I have the feeling the promise of blockchains will fall short. So if we want Web3 to shape the internet's next chapter, we need confidential compute, and that's what we're building, a network for encrypted compute. One that lets you collaborate without exposure. One that keeps privacy and verifiability really together. And one that should be as seamless and universal as HTTPS. It's quite an ambitious plan, and it won't happen overnight, but it's essential and it's possible. Now let's dive a bit deeper into the technical aspect of this and why we can't build a network for encrypted compute with CK alone. If you think about Ethereum like now as this world computer, and Ethereum is like the gold standard for blockchains, it's essentially a censorship-resistant, permissionless, globally accessed computer we all trust. And how do we gain this trust, or how do we trust this? It's by implicitly making all data public and agreeing on it in a sophisticated form. But for most applications, what we actually need is something like a trusted compute and storage environment inside this world computer that nobody can look into, but still has the same properties that we would expect from a blockchain. For quite some time, the narrative, as I told you, was that CK will solve this, but this isn't true. Why? What is like the fundamental fact why this can't be done with CK alone? It's because whoever generates the CK proof needs access to all the underlying data. Now, who should be this entity? We are sending all the data and then does the proof. Are these the validators? Like if the validators get all our data, we are back to like making everything public. And that breaks the whole point. Now, we know that CK brings us private state. How does this fit in? Like we know about Aztec, Alio, Maiden. This private state is owned by the user. The user generates the proof using their own data, and this works quite well, and you can build a lot of nice applications. We're seeing a lot of them today or in the workshops. But this form of private state is fragmented. It's fragmented by users. So the moment you want to build something collaborative. And collaborative is not very abstract. Like, think about a decentralized exchange, about a dark pool, about a dating app, something that has something to do with matching, for example. At this point, you have to open up the private state to the application, basically the operator. And as soon as you do that, your private state becomes public again. So what we need, in addition to this user-owned private state, is a private state that is not known to anyone. It's a state we call private shared state. And this is what enables collaboration without exposure. That's the missing infrastructure we need. So how do we actually build such a network for private shared state? Let's start with the obvious properties we want. It should hold private data, or private state that is not known to anyone. It should allow us to compute on private state, although nobody knows it. And the state update that results from this computation should be verifiable by anybody, including, of course, blockchains. So in short, we need persistent, encrypted, verifiable compute. The probably easiest way to realize such an infrastructure would just literally mean using trusted execution environments. But if such a critical piece of the infrastructure, we do not rely on trusted execution environments. So instead, we want to rely on cryptography, having this layer more robust. And for verifiability, the obvious choice is CK. And for computing on multiple inputs while keeping them secret, that's the field of multi-party computation, or short MPC. And when I say MPC, I mean this rather broadly. I don't mean any specific protocol. And like, you can look at, for example, FHE as a two-party MPC protocol, so it fits also like into this field of cryptography. Now, combining CK and MPC seems like quite a headache. Both are fields that are quite complex, quite an overhead. Now you want to like merge them together. This can't be good. But against intuition, combining them can be surprisingly efficient. Like, this was first shown in the original paper, in the original collaborative SNARKs paper, or short co-SNARKs, by Alex and Dan Bonnet. Like, the TLDR, the main insight is, like, if you look at zero knowledge proof generation from a computational point of view, it's mostly linear operations. So, and you have to know that those linear operations do not introduce overhead in MPC systems. So this paper really showed us a way how to combine encrypted compute and verifiability in a practical manner. And at TACEO, we have been working on co-SNARKs for the last 1.5 years. We first presented our ideas at like the CK Summit 11, a bit more than 1 year ago, and then started to build tooling, like a proof of concept in Circum, so that you can compile any Circum circuit to a co-SNARK. Since that proof of concept, we have been focused on what we call co-Noir, and that's why we're also here. Like, co-Noir is a way to build co-SNARKs in Noir. And like, if you're interested, like, this is already live, you can use it, and there will be a workshop at 12:15 later down in the small workshop room. Now, this was a lot of words, and of course, a big vision. Visions are only like meaningful if you can ship. So I want to share with you the concrete next steps that we are taking at TACEO to make this network real. We're only a few weeks out from launching our production network with its first use case, private proof delegation, under the product name TACEO Proof. It will be for CK apps and protocols that suffer from bad UX due to long client-side proving times. At launch, we'll support Circum, but closely followed from Noir. And later this summer, we plan to integrate fully into the Aztec network, which then enables any application on the network to just use TACEO Proof out of the box and get a great UX while still preserving privacy when they generate the proofs. Like, as you see, this first phase of the network is kind of ephemeral. Like, it doesn't persist data between states. So we'll upgrade the network later this summer that it can hold persistent encrypted state. And this will make an evolution from a CK as a service network to a comprehensive encrypted compute solution. And the biggest leap forward will happen towards the end of the year. This is then private shared state at large scale. At the core is a primitive we're calling oblivious sparse Merkle tree. So it's like very similar how Ethereum interacts with data and stores data. It would enable an efficient encrypted reads and writes on secret shared data, at the scale that is needed for real-world deployments. And it will serve as like the foundation for private shared state deployments across the Ethereum ecosystem. So that's the Papillon, from private proof delegation to persistent encrypted state to private shared state. But it's not just a technical roadmap for me. It's a bet on what kind of internet we want to build. Because without encrypted compute, we're kind of stuck. And coming back to my initial question and how this question is now perceived, I see that people react differently. Like if I talk about them, like about the limitations of CK, and like if they feel we have to build this confidential compute in order to reach our common vision. And this has really changed over the last 2 years. Like one example is like I'm getting a slot here to talk about this to you for 20 minutes. Now, to close, I want to say like we have managed as a community to build public state, and we're just witnessing how to master private state thanks to Aztec. There's just this one frontier left, the one thing we have still to master in order to have widespread real-world adoption, and it's private shared state. And with CoSNARKs, with MPC, with this network, and like with the help of this community, we finally have a real shot at changing that. We can give people and applications the ability to work on private data together without giving up control. And it has to become as universal, as seamless as HTTPS in the end. And that's what I'm building, and we couldn't be more excited that our journey and the journey of CoNoir and private shared state started really in the heart of this community. Thank you.
Hey, great technology. I have a question about oblivious sparse Merkle trees. Do you have some limitations in how you access the state? Like, for example, in fully homomorphic encryption, you can do this additions and multiplying by scalar, or is it completely arbitrary interactions?
It will be completely arbitrary actions, but like the oblivious sparse Merkle tree is something that we haven't disclosed so far, so it's the first time mentioned in public, and like it's still under heavy development, but it's like a general purpose program, like how you would usually interact with a Merkle tree. At the beginning, it mostly read, writes, updates.
Cool, thanks.
Great talk, thank you. I was wondering what type of overhead you have compared to a normal execution on chain, if you want to do private shared state compared to a normal transaction. How does that look? Or do you have communication with the computing committee, or how does that work?
Yeah, so private shared state is handled off-chain. Like you can think of it like this network like just rolls the new state update on chain. So the one thing that happens on chain is like commitments and verifying the proofs that come from the network. So you're technically not like doing too much work on chain. Like if you're for the proving part, like going from normal NOR to CoNoir, like there is like no theoretical overhead that we occur, or very little, as like most operations are linear. There's still like some engineering work to catch up with the great NOR team, like all these performance improvements you have to kind of translate also to the MPC world. And for private shared state, like the biggest bottleneck that you want to get right is what we call the witness extension or the witness generation. Like this part of the proof generation that does the plain execution of the program now has to happen in an MPC network, which is like the biggest bottleneck.
And for the user themselves, do they have to do anything else when they want to post a transaction, for example?
No, like for the users, they don't like see if it's private shared state or like it's private state or public state. This doesn't change anything. It's for the developers, and they're like, that's why we target in NOR, that we do not introduce a new way how they have to think about programs.
Hi, thanks for the talk. I'm curious if you consider a viability of introducing a peer-to-peer private shared state, because this is what a dark pool is. So you still have an intermediate in the form of a blockchain storage. So have you considered the ability to operate without this?
You mean like that the MPC network is really peer-to-peer between like all the participants? Yes, like
the state exists only there.
yeah, we have considered it in the design space. Like it's quite hard because like everybody has to be online all the time, or like you can do some asynchronous protocols, but like you're then limited by the bandwidth, by the latency of every single individual that participates in this network. It would be great if we get there sometime at some point. Like this would be like the ultimate end goal, like to have like a network of users like peer-to-peer. Engineering rights is, I guess, like the hardest part that you can target for.
Thank you.
Thanks, Lukas.
Thank you for having me.